Dear students, please write down the heading work and energy. Work, work and energy. So first we will study about kinetic energy. I am referring the book H.C. Verma, Physics Concepts of Physics Part 1. A very nice statement is written here. A dancing running man is said to be more energetic compared to a sleeping snoring man. That is true, definitely. In physics, a moving particle is said to have more energy than an identical particle at rest. Is it always true? In physics, a moving particle is said to have more energy than an identical particle at rest. Suppose if a particle is placed at a lot of height, then it is having some gravitational potential energy. And if we compare another object which is moving with some velocity, then it is having kinetic energy. It can always happen that the gravitational potential energy, in spite of it not being in motion, not having any velocity, the object having the gravitational potential energy is having more energy than an object moving with the velocity v. So this statement is partly untrue. Quantitatively, the energy of the moving particle over and above which energy is defined by kinetic energy equal to half mv square is to half mv dot v. Kinetic energy is defined in such way, half mv square. There may be a derivation for this formula, but exactly I also don't know the derivation. So the kinetic energy is half mv square, it is half mv dot v. And this is called the kinetic energy of the particle. The kinetic energy of a system of particles is the sum of the kinetic energy. Now, if there is a system of particles in a arrangement, in a system, there are many particles, say I. So the total kinetic energy will be the summation of all the kinetic energies. It is given by summation I half mi vi squared. The kinetic energy of a particle or a system of particles can increase or decrease or remain constant as time passes. If no force is applied on the particle, its velocity v remains constant and hence the kinetic energy remains same. If no force is applied on the particle, its velocity v remains constant and hence the kinetic energy. See, the velocity will change only if you apply a force. There will be an acceleration, a constant acceleration if the force is constant, and if the force is variable, then the acceleration will also change. So there is a change in velocity only on the application of a force. This is the Newton's second law. A force is necessary to change the kinetic energy of a particle. If the resultant force acting on a particle is perpendicular to its velocity, the speed of the particle does not change and hence the kinetic energy does not change. Kinetic energy changes only when the speed changes, and that happens only when the resultant force has a tangential component. When a particle falls near the Earth's surface, the force of gravity is parallel to its velocity. Its kinetic energy increases as time passes. On the other hand, a particle projected upward has the force opposite to the velocity and its kinetic energy decreases. From the definition of kinetic energy, now we are differentiating the kinetic energy to find the power. See, the differentiation of energy is always, with respect to time, always gives you the power. So if we differentiate dk by dt, we will get d by dt half mv squared. We differentiate it. So what we will get? Half mv into 2v. This is cut and it is dy dv by dt. So we will get ftv, where ft is the resultant tangential force. If the resultant force makes an angle theta with the velocity, then ft is equals to f cos theta, dk by dt equal to f cos theta, f dot v equal to f dot dr by dt, dk is equals to f dot dr. Write down the formula. The change in kinetic energy will be given by f dot dr vector. Now we will discuss the work and work energy theorem. Put the heading work and work energy theorem. Work and work energy theorem. The quantity F dot dr equal to F dr cos theta is called the work done by the force F on the particle during the small displacement dr. The work done on the particle by a force F acting on it during a finite displacement is obtained by W is equals to the integration of F dot. There is a lot of maths in it. मैथ्स बहुत ज़्यादा है. मैथ्स तो थोड़ा बहुत तो करना पड़ेगा ना, क्योंकि हम फिजिक्स कर रहे हैं तो हमें मैथ्स का नॉलेज तो चाहिए ही. मैथ्स के बिना हम डिस्क्राइब कैसे करेंगे? इज इक्वल्स टू इंटीग्रेशन ऑफ एफ कॉस थीटा dr, where the integration is to be performed along the path of the particle. I am sure you all have done your course on maths on the calculus course. Have you all done the calculus course? Differentiation, integration, have you all done, or do I need to show you? I think you must have done in your maths differentiation and integration. Okay. So I'm assuming you are aware of differentiation and integration. When the integration is to be performed along the path of the particle, if F is the resultant force on the particle, we can use equation 8.2 to get W is equal to integral of F dot dr equal to integral dk equal to k2 minus k1. Thus, the work done on a particle by the resultant force is equal to the change in its kinetic energy. This is called the work energy theorem. Let F1 vector, F2 vector, F3 vector be the individual forces acting on a particle. The resultant force is the vector sum of F1, F2, F3, etc. And the work done by the resultant force on the particle is given by work in integral of F dot dr is equal to the summation of the F is equal to F1 dot dr plus F2 dot dr plus F3 dot dr, where equal integration of F1 dot dr is the work done on the particle by F1 and so on. Thus, the work done by the resultant force is equal to the sum of the work done by the individual forces. Note that the work done on a particle by an individual force is not equal to the change in its kinetic energy. The sum of the work done by all forces acting on the particle, which is equal to the work done by the resultant force, is equal to the change in its kinetic energy. The rate of doing work is called the power delivered. The work done by a force F in a small displacement dr is dw equal to F dot dr. Thus, the power delivered by the force is P equal to dw by dt F dot v. Okay. Now, calculation of work done. Here again the same formula is given, F dot dr. Now, let us discuss about constant force. Suppose the force is constant in direction and magnitude during the displacement, then W is equal to F dot dr is equal to, if it is constant, we can take it out of integration. We can take F vector out of integration and then we can integrate it, we come to F dot dr, where r is the total displacement of the particle during which the work is calculated. If theta be the angle between the constant force F and the displacement r vector, the work done is equal to W equal to Fr cos theta. In particular, if the displacement is along the force, as is the case with the freely and vertically falling particle, theta is equal to 0 and W is equal to Fr. The force of gravity is constant in magnitude and direction if the particle moves near the surface of the earth. Achha, I was asking about maths. So, can you tell me what will be the differentiation of sin x? What will be the differentiation of sin x? Can you tell me? Anyone? Differentiation of sin x will be cosine of x. And what will be the differentiation of cosine of x? It will be minus sin x. What will be the differentiation of x square? It will be 2x. Of log x, 1 upon x. Differentiation of 1 upon x minus 1 upon x square. So these formula, you don't need to memorize this. You have to learn differential calculus first. In particular, if the displacement is along the force, as is the case with the freely and vertically falling particle, theta is equal to 0 and W is equal to Fr. The force of gravity mg is constant in magnitude and direction if the particle moves near the surface of the earth. Suppose a particle moves from A to B along some curve and that AB makes an angle theta with the vertical as shown. The work done by the force of gravity during the transit from A to B is so and so. This you can study on your own from the H.C. Verma book, Concepts of Physics Part 1. spring force. Consider the situation shown in figure 8.3. One end of a spring is attached to a fixed vertical support and the other end to a block which can move on a horizontal table. Let x is equal to 0 denote the position of the block when the spring is in its natural length. We shall calculate the work done on the block by the spring force as the block moves from x equal to 0 to x equal to 1, x1. Draw system. Draw the spring, draw the block on the wall, draw these things and show the motion from x equal to 0 to x equal to x1. So I'm just drawing it. This is x equal to 0. This is x equal to, say, x1. This is a, and this is a. The force on the block is k times the elongation of the spring, but the elongation changes as the block moves and so does the force. We cannot take f vector out of the integration f dot dr. We have to write the work done during a small interval in which the block moves from x to x plus dx. The force in this interval is kx and the displacement is dx. The force and the displacement are in opposite direction. F dot dr equal to minus fx f dx equal to minus kx dx. During this interval, the total work done as the block is displaced from x equal to 0 to x equal to x1 is total. We have to calculate the total work done. If the block moves from x equal to x1 to x equal to x2, the limits of integration are so and so. This you have to do it on your own. Force perpendicular to velocity. Suppose f is perpendicular for velocity for all the time, then f dot dr, f dot dvt is 0 in any small interval and work done. If there is a velocity, if an object, say this pen, is moving with the velocity in this direction and there is an upward force acting on it, not in the direction of the velocity, there is no component along the pen, along the movement of the pen, so the net work done in that case is 0. For example, if a particle is fastened to the end of a string and is whirled in a circular path, the tension is always perpendicular to the velocity of the particle and hence the work done by the tension is 0 in circular motion. This is an example for circular motion. Thank you. We will meet in the next class. Thank you.